I'm not doing right now is that, oh, where'd it go? I misplaced it. Over here on this board, I had that equation where it was the sum of all these sources that were out of phase with one another. And they were out of phase in a systematic way. Each time the source was out of phase by, let's call it delta, right? And then delta, 2 delta, 3 delta, 4 delta, as they go on some way. I just want to point out to you that that problem, the one that I've done here, all right, is essentially identical to this problem, where I've got an array of atoms like so. Now I just call them atoms. Right? And then I send X-rays in. And the wavelength of the X-ray is comparable to the distance between the atoms. With the result that the scattered wave, remember you just did a problem where you had an electromagnetic field incident upon an electron, and the electron oscillated, and that gave rise to a scattered field, right? The scattered field from each of these, they're all out of phase by a certain amount. And there's a certain number of them in this direction. Let's say that there are n of them. They're all emitting equally, and you're detecting them out at some point, right? Which means that the signal that you're going to see out there is going to be proportional to the number of scatterers squared, right? And the peak that you're going to see out here is going to be an extremely sharp peak, because normally this number here is, even for a nanocrystal, it's of order 30,000, right? So you're going to see an extremely sharp peak at a particular angle, and then you'll see an extremely sharp peak at another angle. And all the other stuff is in there, but the ratio between that and that is like 1,000,000. Right? So X-ray diffraction and crystallography is based upon the idea of multiple scatterers. Right? The larger the sample it is, the sharper this peak is. For those of you who've seen a little bit of this, maybe in modern physics, the width of this peak depends inversely on the number of scatterers or the size of the diffraction sample. And that width has a name. The Debye-Scherrer width, right? Which is, if you look at the width of the diffraction peak that you see in X-rays, it tells you how big the sample was that you were scattering from. Or not actually so much the size of the sample, but it tells you how large the crystallite within the sample was that you're scattering from. So the width of the diffraction peak is inversely proportional to the linear size of the sample. You can measure the size of your nanocrystal, for example, by just measuring the width of the diffraction peak that you see from that. Right? But wait, there's more. So X-ray diffraction, we just did it, right? That same arithmetic that I just did here is what's used in multiple beam reflection.
No, put it in front of the camera.
Right. All right. Multiple beam reflection in optics. So basically, I have two surfaces, and then I have a beam incident, passes through, comes back out, I get reflections. Phase shifts upon each reflection, and phase shift due to the extra path length. Right? You add up all those things, what do you get? The thing that's going around might be, oh, no, okay. Sorry, I have another image here. So, in the notes that I have not yet posted, but I'm about to post, there are some clearly labeled notes that are called supplement at the top, right? Last year I did this as part of the course, but I don't have time this time around. So, I'm just putting these in the notes for your reference. Actually, I think that this is maybe the only place that I've seen, that's why I bothered to do it, where somebody took and pulled all those phenomena together and showed how the arithmetic in every one of the cases is the same arithmetic, the results are the same, and when you have multiple, what?
Fundamentals of optics.
Did you do phased arrays? Oh, yes, you did. Okay, you were never supposed to have worked at that level in fundamentals of optics.
But we had Schroeder.
But I will comment that where I put it all together so that I understood the connections between all of these was when I was teaching fundamentals of optics and advanced optics and nonlinear optics at the graduate level and solid state theory.
So what we call fundamentals of optics now.
Yeah, fundamentals of optics is supposed to be a sophomore level course in which you actually do not do partial differential equations at all. Your hand is just hanging there, right? Okay. Multiple reflections, which are commonly called cavity reflections. And then in the notes, I have calculated the transmission through Fabry-Perot cavity, right? So that's in here. And again, Schroeder probably did it. Fabry-Perot is like his second favorite thing ever.
Yeah, sounds familiar.
Yeah. So he probably did do it, but again, I did the arithmetic clearly here. Actually, he probably, I'm sure he did it clearly in the notes.
Just between pages he switched notation.
Oh, okay. Then in the supplement, I did it for unequal fields. All of these were for equal fields. So that's all just available to you in the notes. You don't need it for this course. Anything that says supplement, you're not responsible for.
That's cool anyways.
Okay. Yes, plenty of time for yet another entire topic.
We hope.
The idea here, actually, I don't know whether it came across because I wrote a lot of junk on the board, right? Is really very simple. And it's that when you have sources that are close together compared to the distance of observation, the only thing that's important when adding those two sources together is the phase difference between the two sources. The phase difference, from the electromagnetics point of view, arises from the retarded time, right? From the continual wave point of view that you would use in physics 2 or in optics, it just arises from path length. Okay? But the origin here is in that T prime. Because all of these phase differences came from the path length difference, which appeared in T prime. Okay? So the key idea here is really pretty simple. And then you put it all together and you get all this fancy and useful behavior. Yeah, and most importantly, by the way, so phased array radar really important for pinpointing where an object is, right? But more importantly, it's really important if you have a whole bunch of ultrasonic emitters and you put them on somebody's side and you aim them and phase array them just right, you can put the maximum in the ultrasonic amplitude intensity right where the kidney stone is.
By kidney stone. What kidney stone?
He had one when we took physics 2 with him.
The one that you
There-
No, that's
Let me say I'm
the joke
new
is
when it's remains.
it makes it look like there's one
left
there.
the theater.
It doesn't matter. Kidney stone. Which hurts a lot.
Yes.
Yes. Hurts like hell.
Okay. I feel bad that I'm not going to spend enough time on Kirchhoff radiation. But
We've
we'll
had,
do that next class.
some of us have had optics.
What?
Some of us had optics.
Yeah.
Some of us have not.
Meh. Go take optics, noob.
I was taking
Okay.
organic chemistry. It was a joke.
So,
We're not supposed to have done that
Um,
either.
one more application topic that two more application topics to go, right? One that I'm going to talk about now are electromagnetic waves in a metallic cavity. Right? And so waveguides and cavity oscillations. And then this will probably run over a little bit into the next class. But then the next class I will do essentially single slit diffraction. Just so that you get an idea as to where all these things come from. I guess I should comment that because I'm actually not giving you homework on this material, I will probably have, let's say, a number of conceptual questions related to the conclusions of the calculations. You know, what do the modes look like? Where's the maximum intensity? Things like that. In either sort of short answer or multiple choice form. So you will be examined on this material. You should read the notes and make sure that you understand it as best you can without solving problems. Right? But I can't examine you on tougher solved problems without really practicing you on those problems. So,
It wouldn't be.
electromagnetic waves in a cavity in a metal. What do we know? Right? In the space, there's nothing but the waves. And so that means that in the space, I have Maxwell's equations. And so Faraday's law. And Ampere's law, or Maxwell-Ampere law, the Maxwell part of Maxwell-Ampere law. And from that pair, we can deduce a wave equation that has to be satisfied. I'll write one of them down. The other one is the same. Oops. And the same for the magnetic field. Right?
D
So
squared,
when-
dt squared?
Yes. That was the Schrödinger equation. With the wrong constants. Yeah, it would have been the wrong constants. All right.
Somewhere the
And
constants were right.
we're going to seek solutions. We're going to We're going to seek solutions that oscillate harmonically, because we can just create any pulse solution that we like out of solutions that oscillate harmonically. So what do I know? I'm going to seek a solution. The magnetic field will be the same. A space part and a time part. And so the wave equation is going to look like this. Del squared E minus omega squared over C squared E is equal to 0. I said minus, but I switch it to a plus because when you take the derivative twice, the I might be a minus sign, right? So this is really 3 equations for each component of E. 1 for each component of E. And 3 more for each component of B. Right? And these are multiple equations as well. We have to satisfy it component by component. So when we consider them all together, we have 6 eigenvalue equations that have got to be solved for any problem, right? And E and B are not independent of one another. We know how they've got to be related. Okay? So, and although I've assumed oscillating solutions, I have not assumed traveling waves, electromagnetic wave solutions. When I have a simple traveling electromagnetic wave, the electric field and in vacuum, the electric field and magnetic field have got to be in phase and perpendicular to one another. when I don't have a traveling wave solution, but I actually have a standing wave or some other, well, it will be a standing wave solution, some other solution, it could be a sloshing wave solution, right? Then the electric and magnetic fields do not have to be perpendicular to one another, and they do not have to be in phase with one another. Okay? So what we're really going to do here, is take this set of equations, and we have to apply appropriate boundary conditions to the electric and magnetic fields, right? What are those boundary conditions? These boundaries here are metal. And now we ignore the properties of real metal that we talked about, where the electromagnetic field actually penetrates some distance into the metal. We've got a skin depth. We say the skin depth is 0 because it's small, usually. Let's say for microwaves, we're talking microns, and the wavelength is, in vacuum, is centimeters. So it's very small. We're going to just treat these as ideal conducting metal walls. Right? And that tells you that at any boundary, at any one of these boundaries, the electric field parallel to the boundary is 0, and the magnetic field perpendicular to the boundary is 0. Magnetic field perpendicular to the boundary is 0 because basically if I have a magnetic field coming into the surface, it's going to generate surface currents. Perpendicular, it's going to changing magnetic field, generate surface currents, which are going to drive the magnetic field to 0. And actually, you could make that argument for the electric field too. If there's a field present, a current will be generated in order to move charge, in order to cancel the field inside the material. And the electric and magnetic fields have to be continuous. All right. The general problem here is hard to solve. So I'm going to address some special cases. The way I'm going to start is by addressing the case of what's called a right. Somebody tell me, it looks like 1L. A right cylinder.
Looks right. No pun
It's not a
intended.
circular cylinder or a rectangular cylinder. What we actually mean is that the cross-section, whatever it might be, so it could be shaped really funny, right? But it's the same everywhere down the length of the cylinder. That's the only condition that has to be met. The sides are straight, and any line along the side is going to be parallel to another line along the side. Okay? If we do that, then the problem becomes more manageable. But then the next stage that I'm going to take after I've sort of set up the right cylinder problem is to specialize further still and say, let's just talk about, I think I decided to do a right rectangular cylinder because it's, and then we'll do just a rectangular metal box. Right? I've forgotten what that's called, rectangular parallel pipette. You need, it's a three-dimensional box, so it's not a rectangle.
Rectangular
Where are the
prism?
mathematicians here who always remember
Sounds like rectangular prism. Or a
rectangular prism? Okay.
I mean, if we're assuming they're all right angles, if you've got angles that are slightly skewed, then it turns into a parallelepiped, yes.
There we go. Okay. So,
Don't look at me, I haven't taken
the
topology.
cross-section can be arbitrary, but it's got to be constant. We're going to take the z-axis to be the longest axis. Right? We're going to assume that the z-dependence can be represented, let me see. Yeah. Actually, I'm going to start out with cavities. There's a wall here and a wall there. Okay. And putting those two walls there enables me to assume that the z-dependence is just a Fourier series. Okay. So, the electric field then is going to look like this. And now I can explicitly, actually, what I coulda, shoulda, woulda done is to write down the general wave equation and then do separation of variables term by term. But I'm just going to write out the station here, because we've done that enough. So I separated out the z-dependence explicitly, right? If the box is finite, then k sub z is only allowed to have certain values. Just by, oops, I lost the direction of the field. Yeah.
Does the plus and minus mean you're actually multiplying that function of x and y times e to the negative I omega t plus kz plus e to the minus I omega t minus kz?
No, it's one plus the other.
So you're saying there's...
I could have a wave going this way and or a wave going that way. So it's not the product. I'll tell you what. Let me see how far I can get.
Where you have to decide what way it's traveling?
Yeah,
Okay.
let's do that and see how far we can get.
Alright.
Okay? So, for now, I make it right circular, an infinite right circular cylinder. It's not cylinder then, tube. You know what I'm saying? Correct. A pipe. So, in my notes, I have written then the 6 equations. And I am going to write out a few of them. dBz, dy, these are curl, minus I, k, dy equals minus I omega over c e x. So basically, oh yeah, I can tell you. What we're doing is just plugging, we've got 6 equations here. All right? So I've got, and that's not the one that I just did, that's this one. Okay? And because the derivative of the magnetic field in the z direction is kz times the minus kz times the magnetic field, that's where that comes from. There's an I in kz. That's where that comes from. This comes from the time derivative. So it's because I've assumed an oscillating traveling waveform here that I get that expression. All right? I could have I, k, dx minus d. I'll write down one E equation. Dx equals dy. And one electric field equation, just because there are 6 of them, I don't need to write them all out. I, k, dx minus d, dx, dx equals I omega over c dy. And I have to satisfy these boundary conditions at each surface. There are a variety of ways of tackling the this problem, actually.
Is that part D east of X over dx?
I was just giving you, I probably wrote it correctly, but it's actually, I'm going to spend a lot of time doing that in this class, right? I wrote them all out in the notes.
Please don't do that. I'm actually gonna want to copy these.
Still wants to be
Then you
online.
can
I'll post them
pause the
online.
video.
Also in Ohanian.
I know.
They're all in Ohanian, by the way.
I was deliberately doing this.
I know.
And if you pause it, you can't read anything. There's not enough pixelization.
Yes. All right. So it exists. I did it.
Yeah.
Copied it straight out of somewhere.
Oh, probably Ohanian.
It doesn't speak about it.
Is it in Ohanian?
Yeah, there.
Okay. I copied out of it. But what we're going to do is solve for the other components, the x and the y components, in terms of the electric and magnetic fields pointing along the z direction. So yes, indeed, even though, well, actually here, yeah, even though nominally the wave is propagating along the z direction, there are electric and magnetic fields, there will be magnetic fields along the direction of propagation. They're allowed to be. Okay, so I can solve for the other components of the field in terms of EY and BY, and then figure out what conditions apply here. So E sub x, yes. And all we're doing is putting all those equations together. Omega squared over c squared minus a squared times. For the propagation direction that I've chosen is plus I, k, d, e, z, dx plus I omega over c d, e, z, dy. And x, c. Yes, good. Yes, I will do this. All right. I'll do one more step and then we'll go outside. I can use, for that direction of propagation, IK EZ is equal to DEZ EZ. Did I lose it? No, that's good. So that means that I can make substitutions in here for EZ, IK EZ, and I end up with this. EX is equal to 1 over omega squared over c squared minus k squared. D squared EZ dx dz plus I omega over c dz dy. I could do the same for the EY, BY, and BX relations. So I have 4 equations. And those 4 equations need to satisfy the boundary conditions for this box. Yeah, okay, actually, then I'll just make one statement and then finish for now and continue next time. All right, here's where we come down to what we needed to do at the ends. I've got this right cylinder, and I have chosen to put a wave that's propagating in this direction, right? But if I make boundaries here, then I'm going to get waves propagating in both directions, and the solutions are going to have specific forms. But they're not going to be hard to solve because I'm only solving one direction for the z components, right? So I can write down that del squared Ez equals minus omega squared over z squared Ez. So that's the electric field along the the channel, right? The electric field's got to be 0 on the sides. And so if this were, for example, a rectangular waveguide, a cavity, then the EZ field would have to be 0 here and there, and therefore it would have a sign, if this were x, I would have sine kxx solutions, where kx would have to have specific values that will be quantized. Right? I'm going to have that, or I just misdrew that, but you get the idea, right? Which you've done bazillions of times in quantum mechanics, for example. So those are my allowed solutions in this direction. For the field in the z direction, the electric field in the z direction. Okay, I can solve this equation for the magnetic field in the z direction as well. But in order to fully solve it, I have to know what the boundaries are on the ends. Okay.
So without the boundaries, you can get everything in terms of EZ.
Yes. You get everything in terms of EZ, but you haven't solved for EZ yet.
Right.
All right? So next class, we're going to take specific cases and solve for EZ and then BZ. And then from that, we can deduce all the other fields.